Graphs of sine and cosine functions. First, we start by defining a periodic function. A periodic function is a function returning to the same value at regular intervals or periods. So in our first example, find the period of each periodic function shown below. So in this first graph, we can see that the graph just repeats over and over again. So we are looking for the period of this graph. So we want to identify, well, when does it start over again? So the general shape of one period, informally, to me, looks like a little shark fin with a tail. And then it starts to repeat over again. So I have another little shark fin with a tail. So the period itself is the horizontal distance required for the periodic function to complete one cycle, or in this case, one little shark fin with a tail. So here, the period would be 2 units, right? That horizontal distance from 0 to 2. So we can see the next one is between 2 and 4, also 2 units. So the period here is 2. For this second periodic function, I'm going to go ahead and start by looking at where the function is at the x value 0. So it's up here on the y-axis. And then I'm going to go ahead and trace the graph until I reach that same value again, where I can see it's going to start to repeat at that point. So this would be considered one period of the graph, and we want to measure that horizontal distance it took to complete that one cycle. So we started at the x value 0 here, and we come over here and finish at the x value not quite 6, so we can see that maximum point there doesn't quite line up with 6, it's a little bit past 6. And in fact, the value is 2 pi. So remember, pi is 3.14, so this is approximately 6.28. So the period here that we're going to identify is 2 pi. Let's look at the sine graph. F of x equals sine x. So this is a function. We can go ahead and substitute in different values for x into sine x and get out corresponding y values. So the types of values we can plug into the sine function are angles. So I've gone ahead and thought about plugging in my quadrantal angles into sine, and these are the respective values that we get out. And each of these corresponds to a coordinate point. So we have the graph of sine here, and let's see how it matches up with our table of values. So here we have the coordinate points labeled that correspond with each of these pairs, so 0, 0, pi over 2, 1, etc. Now, this is only highlighting 5 key points on one period of the sine graph, but the sine graph is, as you can see, periodic, and it does in fact go on forever and ever in both directions. And that we're going to refer to as its domain. The domain is the x values on which the function exists. So this says all x values in the interval from negative infinity to infinity. So this is just going to keep going on over and over again. The range is all the y values that come out of the function. So this is between -1 and 1, including -1 and 1. So the lowest y value that comes out, the smallest, is -1 down here, and the biggest y value is at +1. So notice that the sine graph passes through the origin, 0, 0, and then starts to go up. From there, identify the general wave shape of the 5 points on a period of the sine graph. So there are obviously infinitely many points on the actual graph itself, but these are the 5 key values that we want to identify: the maximum value, and the minimum value on each interval, and all of the x-intercepts. Those are those 5 key values that we want to identify on any sine graph. Now let's look at the cosine graph for the function f of x equals cosine x. So once again, we have a function. We can substitute in x values, those x values being angles. We've chosen the quadrantal angles again. And then here are our outputs, our f of x values. So after substituting 0 into cosine, cosine of 0 is 1, and so on for the remaining angles. And then again, each of these corresponds to a coordinate point on the graph that we have here for the cosine function. So let's show that matchup. So we have 0, 1, the coordinate point. We have pi over 2, 0. We have pi, -1. 3 pi over 2, 0. and then 2 pi 1. So the domain, just like the sine function, is all real numbers, so this graph is going to repeat over and over again. And the range is the same as well. From -1 to 1, those y values are going to extend. So the difference here, if you notice, the cosine graph passes through 0, 1 and starts going down. And from there, we want to identify the general wave shape of the 5 points on the cosine graph. So this cosine graph starts up here on the y-axis at 0, 1, and then starts traveling down to the x-axis, goes down to this minimum value of -1, back to the x-axis, and then back up to 1 again, where it's going to repeat forever and ever because the domain is all real numbers. Graphing transformations of sine and cosine. So let's say we're given y equals a sine bx or y equals a cosine bx. We say that the absolute value of a is called the amplitude, and on the graph represents the height of the wave. So we can see here that the amplitude is the height of the wave. So in either direction, we consider the height a positive number. That's why we take the absolute value. And the period of the graph is 2 pi over b. So that's the formula for finding the period. So that's when I have a value here in front of x, a number other than 1, and then we have 2 pi over that number. So the period formula is 2 pi over b, and that's 1 full wavelength. And if a is a negative value, then the graph reflects or flips over the x-axis. So if a is a negative value, then the whole graph is going to flip over the x-axis. Let's jump into an example. Graph 2 periods of y equals 2 sine 3x. So first we'll identify the amplitude. That's the absolute value of the number in front. So we have +2. The period is 2 pi over the value that's in front of x, so 2 pi over 3. And then we'll answer the next question, is there going to be a reflection? Well, since the number in front of sine is positive, the answer here is no. There will not be a reflection over the x-axis. So what I'm going to go ahead and do now is think about the fact that 1 full wavelength of this sine function will have to start at 0 and end over here at the end of the period 2 pi over 3. So I'm going to have 1 complete wavelength occur between 0 and 2 pi over 3. And we know that the sine function starts at the origin. So I'm going to draw a point at the origin at 0. And what we need to do from here is we need to create 4 equal parts between 0 and 2 pi over 3. So I'm going to cut it in half and then cut each of those halves in half. And we want to label each of these values. So sometimes people are just have good number sense in order to split this up, and that's absolutely fine. I'm going to give you a strategy for breaking this into 4 equal parts. I'm going to find what's called the quarter period. So the quarter period is essentially 1/4 of the period. So 1/4 of 2 pi over 3, which simplifies to 2 pi over 12 or pi over 6. So each of these subdivisions has to be of length pi over 6. So we have 1 pi over 6, 2 pi over 6, 3 pi over 6, and this last one should be 4 pi over 6. And we can see that after reducing that it is. So I'm going to go ahead and leave the rest of these unreduced for now and not really focus on that. So we know that our sine function starts at the origin, as we said, and at the next tick mark, our sine graph went up. And so it's going to go up to the height of the function, and the height of the function is the amplitude. It's going to go up to 2. So I have 1, 2 units, and I'll mark -1, -2. So at pi over 6, my function is going to go up to +2. And then my sine function turned around and went back to the x-axis. So at 2 pi over 6, at the next tick mark, I'm going to end up back at the x-axis. At the next tick mark, I'm going to be at the negative of the amplitude. So I'm going to be down here at 3 pi over 6, -2. and then I'm going to end up at the end of my period back at the origin, back where I started. If I start at 0, then I also have to end at 0. So now let's go ahead and clarify what points exactly are on my graph of 2 sine 3x. So we have the coordinate point 0, 0, so the x value is 0, the y value is 0. Up here we have the point pi over 6, 2. Then 2 pi over 6, which reduces to pi over 3, 0. 3 pi over 6, that reduces to pi over 2, and we're down at negative 2 at that value. And then finally, we end up at, as we said, 2 pi over 3, 0. We end up back at 0. So now we're going to go ahead and graph the second period. We needed 2 periods, and we're going to draw our period to the left because that's where we have space to do so. We could technically, if we had space, go to the right and draw a second period over here, but I'm going to go ahead and just work to the left. So I'm going to use all the same tick marks, but just negative. So I'm going to use negative pi over 6, negative pi over 3, negative pi over 2, and negative 2 pi over 3. And then complete my general wave shape. It should look exactly the same because it is periodic. So here is a second period of my given function. And now to answer the question about domain, the domain is all real numbers. Even though all we can see, all we've graphed, is from negative 2 pi over 3 to 2 pi over 3, the domain of any sine or cosine function is negative infinity to infinity. The range, however, is different. So now the smallest y value is negative 2, and the biggest y value is positive 2. So we'll put closed bracket negative 2 to positive 2 with another closed bracket. Let's go ahead and break down the steps for graphing one period of a sine bx or a cosine bx. So we just went through an example, and first we found the amplitude and the period. The second step was to divide the period into 4 equal subintervals and label, and this requires 5 tick marks starting at 0 on the x-axis and ending at the period. So this step was that quarter period part. Part 3, create the general wave shape using 5 clearly labeled points on the graph. Note that sine functions start at the origin with the general wave shape finding maximums and minimums at a and negative a respectively, but cosine functions start at the amplitude in general. They start at the amplitude with their general wave shape, again finding maximums and minimums at a and negative a respectively. We would then perform any reflections and make sure your graph has 5 clearly labeled points. If necessary, use a table like the one we created. Alright, let's do another example. This time graph one period of y equals 5 cosine of 2/3 x. So the amplitude is positive 5, and the period is 2 pi over, the number in front of x here is 2/3, 2 pi over 2/3. Well, that's 2 pi times the reciprocal, 3/2. So the 2's are going to cancel, and my period is 3 pi. So I'm looking at a value, well, I shouldn't put a point there, but I'm looking at starting at 0 and ending at 3 pi, and I need those 4 equal subdivisions, so I need those 5 points that are key to my graph. So I'm going to need the quarter period again. This time I'm going to abbreviate it as QP. So that's 1/4 of 3 pi, or 3 pi over 4. So each of these has a length of 3/4 of pi. So the first one I'll label as 3 pi over 4, and then 6 pi over 4 to get to the next one, 9 pi over 4, and then finally 12 pi over 4, which does simplify to our 3 pi. Now there is no reflection because the number in front of cosine is positive, so there is no reflection. So now a cosine graph starts up at the amplitude. So the amplitude is 5, so I'm just going to go ahead and label on the y-axis 5, and I'm going to put my point up at 0, 5. And then the cosine function, after starting at the amplitude, goes down to get to the next tick mark where it's on the x-axis. So I'm at 3 pi over 4, 0. And then I go all the way down to negative of the amplitude. So 6 pi over 4 is going to be over here, down here at negative 5. Then back to the x-axis. And then at 3 pi, I have to end up where I started, up at positive 5. So I've labeled my 5 key values, and now I'm going to go ahead and sketch the cosine function. So they should be curves. This should be a curve here. This bottom part should be curved. This should be curved as well. So I'm going to try to overemphasize the curve here and what the shape should look like, because it should definitely not look like a straight line. It should not look like a straight line. So I'm going to go ahead and make these a little bit thicker to really indicate that shape. So now, to really just clarify exactly what points that I know are on this one period, I'm going to fill out the table. So I have 0, 5. I have 3 pi over 4, 0. 6 pi over 4 reduces to 3 pi over 2, negative 5. Then I have 9 pi over 4, 0. And 3 pi 5. So to wrap up, domain is negative infinity to infinity for my sine or cosine functions. The range this time extends from negative 5 and goes all the way up to positive 5 for y value. So bracket negative 5 to positive 5, close bracket. Now let's graph one period of y equals negative sine of x over 4. So the amplitude here is 1. So we take the absolute value of the number in front of sine, so that would be positive 1. The period is going to be 2 pi divided by 1/4. So what's in front of the x here is technically this 1, and so I could think about this 1/4 times x. And then if I multiply by the reciprocal, I end up with a period of 8 pi. And this time there is going to be a reflection because the value in front of sine is negative. So reflection, yes, there will be a reflection. So let's go ahead and mark a value at 0. And in fact, I'm going to put a point at 0 because this is the sine function, which starts at the origin. And then over here, I will label the end of my period, so 1 full wavelength has to be completed between 0 and 8 pi. And then again, we want to split this into our 4 equal parts. Now here, I think this is probably an easy one to where we don't have to actually go through the process of finding a quarter period. So half of 8 pi is 4 pi, and between 0 and 4 pi is 2 pi. And between 4 pi and 8 pi is 6 pi. So that one's a little more straightforward, doesn't involve any fractions. And then the amplitude is 1. So here I'm going to go ahead and label 1 and negative 1. And I'm going to do this in phases actually. So I'm going to go ahead and pretend that I don't have a reflection yet. So the sine graph would start at 0, 0 and then normally go up to that amplitude value at the next tick mark. So normally would look something like this. I'm going to go ahead and fill out those 5 values, but I'm going to go ahead and draw this as a dotted function since this isn't my final answer here. It hasn't taken into account the reflection. So this is the graph of just sine of x over 4, not negative sine of x over 4. So now I'm going to go ahead and think about the idea of reflecting it. So this top part here is going to reflect and be below the x-axis. So I'll still have a point at 0, 0, but then I'll have a point at 2 pi negative 1, and I'll still have a point at 4 pi 0. So it'll look something like this. And then 6 pi will go up to positive 1, and then end up back at 8 pi 0. So this graph here, this solid graph, is the graph of negative sine of x over 4. And we'll make sure we know exactly what points we're talking about. So 0, 0, we have 2 pi negative 1, 4 pi 0, 6 pi positive 1, and 8 pi 0 as my values on the actual final graph. And then let's answer the domain and range. Well, the domain for any sine or cosine function is negative infinity to infinity, and the range, the smallest y value is negative 1, and the biggest y value is positive 1. So the range is bracket negative 1 to positive 1. Graphing translations of sine and cosine. So let's say we're given y equals a times sine or cosine of b times the quantity x plus c plus d on the outside. Now what's new, what's different about this is this value of plus c or plus d, and they each do different things. So the value that's added to x, that c is called the phase shift. If it's a minus c, then the whole graph shifts to the right. If it's a plus c, a positive c, then the whole graph shifts to the left. The value of d that's on the outside of the function, either in the back or it could be in the front, is called a vertical translation. If it's a positive d, it's going to shift the graph up. If it's a negative d, it's going to shift the whole graph down. So we can see here this minus c of a phase shift is going to shift everything to the right. If I have a vertical shift plus d, it's going to move everything up. And we still have our idea of amplitude and of period. In this example, we want to graph one period of y equals 1 plus 3 cosine of 2x minus pi. So first we'll write the general form. So we can see that it doesn't quite match up exactly. So we want to do a little bit of rewriting. We want to put the 1 in the back. We want to go ahead and add that value of d. And the inside of cosine has to be b times the quantity x minus c. So we're going to have to factor out a 2 here. And we get 3 cosine of 2 times the quantity x minus pi over 2, and then plus 1 in the back. So you can see if I distribute the 2 back in, I will get 2x minus pi. But now I can identify clearly my a, b, c, and d value. And just to be clear, don't be tempted to add these together. These do not add together. We have to follow order of operations. So let's label our amplitude, which is positive 3, the number multiplied to cosine. Period is 2 pi over 2, so 2 pi over b, so we get out just pi. And let's go ahead and identify what the quarter period is as well. So the quarter period would be 1/4 of that. 1/4 of pi is just pi over 4. The phase shift. So the phase shift is identified by this minus c value. So that's why we had to factor it out. We don't want to be tempted to say the phase shift is minus pi. That's not true. It's minus pi over 2, which means that the graph will move to the right pi over 2. There is no reflection. The number in front of cosine multiplied is positive, so reflection no. The vertical translation is going to be up 1 because I have a plus 1 on the outside. So what I'm going to do is start this in a traditional way, but then kind of stop and think about another method. So if I think about this in a traditional way, I would start by marking my 0 value, the end of my period is pi, and labeling this quarter period values pi over 4, 2 pi over 4, 3 pi over 4. And then going ahead and starting with the sketching of the graph. But the phase shift here kind of changes things for me. I'm going to have to move each and every one of my coordinate points to the right pi over 2. So I'm going to have to move 0 to the right pi over 2, pi over 4 to the right pi over 2. So that's a lot of values that I'm going to have to add pi over 2 to in order to shift everything to the right. So we can absolutely do that. We could finish this thing off and then move each of those points to the right pi over 2. But I'm going to show a different way. This next method is going to involve looking at the part that's inside of the cosine function. So I'm going to go ahead and focus on this 2x minus pi. We could also take the factored version. We could also take 2 times the quantity x minus pi over 2. It doesn't matter. We're going to take that inside part and solve the 3-part inequality. 0 is less than or equal to 2x minus pi is less than or equal to 2 pi. So we're going to take the inside only of the cosine function and put it between 0 and 2 pi and solve for x. So if I add pi to both sides, I'm going to get pi is less than or equal to 2x is less than or equal to 3 pi. And dividing each piece by 2, I get pi over 2 is less than or equal to x is less than or equal to 3 pi over 2. So what I just found was the starting value of my period and the ending value of my period. So now let's go ahead and draw our xy plane. So here we have our start of our period, pi over 2, the end of our period, pi over 2. We still do need to label the tick marks on the inside. And we did find the quarter period was pi over 4, so each of these has to go up by pi over 4 every time. So starting at pi over 2, in order to add pi over 4 to get to the next tick mark, I'm going to rewrite this with a common denominator of 4. So this is 2 pi over 4, making this first tick mark 3 pi over 4, 4 pi over 4, 5 pi over 4, and 6 pi over 4. So now I have my tick marks labeled. I'm going to go ahead and think about the amplitude of the function. Now since this is a cosine graph, my function starts at the amplitude. But remember, the start is pi over 2, not 0. So I'm going to go ahead and label 1, 2, 3, 4. 1, 2, 3, 4 downward. So I have labeled my y-axis values. And I know that I start at the amplitude, so I start at pi over 2, 3. At the next tick mark, I'm at the x-axis. At the next tick mark, I'm down at -3. I'm back at the x-axis, and then I have to end where I started, which is at +3. So this is not the final graph. I'm going to draw it as a dotted function because I haven't addressed the vertical translation. So we said that this whole graph has to move up 1 unit. So I'm going to take each one of these coordinate points and move it up 1 unit. So pi over 2, 4, 3 pi over 4 is going to shift up to 1, 4 pi over 4 is going to shift to 2, 5 pi over 4 will shift to 1, and 3 pi over 2 will shift to 4. And now I'll connect these with a solid graph. This is my final answer. It retains that general wave shape of cosine, but it is not along the y-axis because everything had to shift to the right pi over 2. So solving this inequality adjusted for the phase shift. So now you can see that because we've done kind of so much on one xy plane, the graph could look a little cluttered. So if it's not absolutely 100% clear what points are on my final graph, that's why we create a table. So on our final graph, we have pi over 2 corresponding to 4. So we have pi over 2, 4. We have 3 pi over 4, 1. 4 pi over 4, which is pi, and that's at -2. 5 pi over 4 is at 1, and 3 pi over 2 is at 4. So if I identify my domain, well, this graph does go on and on forever. We just found one period, so -infinity to infinity. But the range of my final graph is from -2 on the y-axis up to +4. So my range is -2 to +4.